Welcome back, students. This is the session 3 from the chapter of current electricity, and the topic is resistivity and its derivation. So here I will be deriving this equation, that is R is equal to rho into L upon A. So this is the equation which relates the resistance of a material, of a conductor, with its resistivity. Rho is called the resistivity of a conductor, and R is the resistance of that conductor, L is the length of the conductor, and A is the cross-sectional area. So I will be deriving this equation in this session. So for deriving this equation, I have written few bullet points on this board. The first point here is that these two conductors, I have taken these two conductors which are identical in nature. These two conductors are identical in nature, means that their material of construction is the same and their area of cross section and the length are also the same. The length of both these two conductors is L and the area of cross section of both these two conductors is A, and they are made of the same material. So therefore they are identical in nature. Second point is I have placed both these two conductors side by side as shown in this figure. Now, if the current which is flowing, let us say the current which is flowing through this conductor, let us say is I, okay, then since both these two conductors are identical in nature and they are also placed side by side, and if the current which is flowing through this combination is I, it means that the current flowing through this conductor, this first conductor, and the current which will be flowing through the second conductor will also be I. Okay. Now here I have considered the potential difference across the first conductor as V. Okay. Here let V be the potential difference across the ends of the first conductor. And now since both these two conductors are identical in nature and the current which is flowing in both these two conductors is the same, therefore the potential difference across the second conductor will also be equal to V. So let's now talk about this combination. So the resistance of this combination, let us say RC, this will be equal to the potential difference across these across the ends of this combination, and this will be equal to 2V. That is the potential difference across the first conductor and the potential difference across the second conductor. I have already written here also. That is, the potential difference across the combination will be 2V, because it will be the sum of the potential difference across each conductor, which has been taken as V. So the potential difference across this combination is equal to 2V, and the current which is flowing through this is I. This is equal to 2 times V upon I. Now, the potential difference across the first conductor and the second conductor is V, and the current is flowing through both these two conductors is the same, that is I. So the we know that V is equal to IR. So R will be, that is the resistance of each conductor will be equal to V upon I, where R is what? It is the resistance of each conductor. So I can then substitute the value of V upon I as R. So I will be getting as 2R. So the resistance of this combination will be 2 times the resistance of the individual conductor. So so from this relation, that is RC is the resistance of this combination of these two conductors which are placed side by side. This is equal to 2 times R. So what we have seen here is, that is when the length of the conductor has been increased. You know, here you can see, here the length of the conductor has become 2L. Okay. So when the length of the conductor has increased, the resistance across the conductor has also increased. So we can say that R is directly proportional to L. So this is the first relation which I have got by using this combination. Here you can see that this effective resistance of this combination is equal to 2R. So now this combination has got a length equal to 2L. L plus L, that is equal to 2L. So we can clearly see that the resistance of this combination has increased when the length of this conductor has increased. So we can say that R is directly proportional to L. So this is the first equation which I have got. Now we will be taking the second case. Now, in the second case, what I will be doing is, let us take the case, this is the second case. In the second case, I will be splitting this conductor into two parts lengthwise. That is, this is the conductor here. So this is the conductor, something like this. So now what I will be doing is, I will be splitting this conductor from the center lengthwise. Okay, now since the area of the cross section is equal to A, so the area of cross section of these two parts, that is, let us say this is the first part and this is the second part. So the area of cross section of the first part will be A by 2, and the area of cross section of this second part will be also equal to A by 2. Now the potential difference across the ends of this conductor has been taken as V. We have already taken it as V. Now the current which is flowing through this conductor is I. So if we split this conductor into two equal parts lengthwise from the center, then the resistance of each part, this will be equal to V divided by I upon 2. Why? The potential difference across both these two parts is V, and since both these two conductors are identical in nature, therefore the current I will be equally split in these two parts. That is, the current which will be the current flowing through the this part 1 will be equal to I by 2, and the current through this part 2 will be equal to I by 2. So the current in both these two parts will split equally. So now so I can say that the resistance of each part of this conductor will be equal to V divided by I by 2. Or we can here say that this is equal to 2 times V upon I. So okay. Now now this V upon I, as we have just seen that V upon I was equal to R. So I will be substituting this value in this equation, and I will be getting it as 2 times R. So in this case, the resistance of each part of the conductor, when it was split lengthwise from the center, becomes 2R. So here in this case, what we have seen that when the area of cross section has reduced, here you can see that the area of cross section has reduced, so the resistance has increased. That is, when area of cross section reduces, resistance increases. From here you can see that here the resistance of each part of the conductor is 2R, and here the area of cross section has reduced from A to A by 2. So when the area of cross section has reduced, the resistance has increased. So from this we get another equation, that is the resistance is proportional to 1 divided by A, that is inversely proportional to area of cross section. That is, when the area of cross section reduces, resistance increases, or we can also say that when the area of cross section increases, the resistance will decrease. So these are the two equations which I have got, and now I will be combining these two equations. So now what I will be doing is I will be combining these two equations, that is combining 1 and 2, combining equations 1 and 2, combining equations 1 and 2. We get R is proportional to, see, R is proportional to length, so I will be writing it here, and R is also proportional to 1 by A, so into 1 by A. So it implies that R is proportional to L upon A. It implies that R is equal to rho L upon A, where rho is a constant. This is a constant which we call as the resistivity of the material. Rho is a constant, and this is called the resistivity of the conductor. So what I have done is I have replaced this proportionality sign with a constant, and this constant is called the resistivity of the conductor. So in this way we have been able to derive this equation, that is R is equal to rho L upon A. Now, so I will be writing this equation here, R is equal to rho L upon A. Now with the help of this relation we can derive some other formulas also. Now we know that V is equal to IR. So this is equal to I. Now I will be substituting the value of R, this R, in this equation. So I will be getting as I rho L upon A. This can be also written as I upon A into rho L. Now I upon A is what? This is called the current density. Current density is basically what? Current density is denoted by J. This is the current flowing through a conductor per unit cross sectional area. That is, it will be equal to I upon A. So I can substitute this value in this equation, that is V will be equal to, if I substitute the value of this J is equal to I upon A in this equation, so we will be getting is another equation, that is J rho L, where J is the current density and current density is the current which is flowing through the unit cross sectional area. So, and it is given by, it is denoted by this J, and J is equal to I upon A. So I have substituted this value of this I upon A in this equation. So I have got this V is equal to J rho L. Now again, if let us say if E is the magnitude of electric field in the conductor, Now, if E is the magnitude of the electric field in this conductor of length L, okay, in this conductor, okay, of length L, then we can also write that now, since V is equal to E into the length of the conductor, and this will be equal to J rho into L. Or we can say that it implies that if L and L will get cancelled out, so the intensity of the electric field is equal to J into rho. So this is another equation which we have got in terms of the current density and the resistivity of the conductor. And this was another equation which we were able to derive, which was V is equal to J into rho into L, and this is the another important equation for all of you to remember. And this is another important equation, that is J is equal to I upon A. This also needs to be remembered by all of you, and this is another important equation which needs to be remembered by all of you. That is R is equal to rho L upon A. Next is current density, which is equal to I upon A. Third is V is equal to J into rho into L. Fourth equation is, that is the intensity of the electric field is equal to current density into the resistivity of the material. And one more thing, there's one more thing, that the conductivity of a there's one more term that is called the conductivity of a conductor. Conductivity of a conductor, that is denoted by this sigma. So this is also equal to 1 upon rho. That is, conductivity is the reciprocal of resistivity. So we can write this equation, that is E is equal to J divided by sigma. So this is another equation which needs to be remembered by you. That is, E is equal to J upon sigma, where sigma is the conductivity of a conductor. So from this session, we have been able to get a number of equations, that is R is equal to rho L upon A, then J is equal to I upon A, then V is equal to J into rho into L, then the intensity of electric field is equal to J into rho, and it is also equal to J upon sigma. So thank you very much for joining this session, and in the next session I will be discussing about the drift velocity of electron. So till then, have a nice day. Bye.